Imagine a place in the universe where gravity is so overwhelmingly powerful that nothing, not even light itself, can escape its grasp. This is a black hole. It is not an empty hole or a portal in the traditional sense, but rather an immense amount of matter squeezed into an impossibly small space. This creates a gravitational field so intense that it fundamentally warps the fabric of space and time around it. Think of it like placing a bowling ball on a stretched-out sheet. The sheet dips and curves around the heavy object. A black hole is the most extreme version of this, a bottomless well in the cosmic ocean from which there is no return once you have crossed its edge. There are two main flavors of these cosmic titans that we have observed. The first are stellar black holes. These are the smaller, more common type, born from the dramatic and explosive death of a massive star. When a star at least 10 to 20 times more massive than our own sun runs out of fuel, its core collapses under its own immense gravity, triggering a supernova. What remains is a compact object, perhaps only about 10 miles across, but containing several times the mass of our sun. These stellar black holes are scattered throughout our Milky Way galaxy, silent remnants of long-dead stars. On the other end of the spectrum, we have the supermassive black holes. These are the undisputed kings of the cosmos, behemoths that can have a mass greater than 1 million or even billions of our suns combined. Their diameters can be as vast as our entire solar system. We believe that one of these giants, known as Sagittarius A*, resides right at the heart of our own Milky Way galaxy, acting as the gravitational anchor around which everything else revolves. They are not just objects in galaxies, they are fundamental to the structure and evolution of the galaxies themselves, cosmic engines of immense power and influence. The true danger of a black hole lies in its event horizon. This is not a physical surface you could touch, but rather a theoretical boundary, the ultimate point of no return. To escape the gravity at the event horizon, you would need to travel faster than the speed of light, which, according to our current understanding of physics, is an absolute impossibility. Anything that crosses this threshold, light, matter, information, is forever trapped. Even a black hole as small as a pinhead could be disastrous for Earth if it passed close enough, its density creating a gravitational pull that would spell our doom long before we reach the event horizon itself. Let us imagine a rogue black hole has wandered into our cosmic neighborhood. As it draws nearer, the first signs of its influence would not be seen, but felt. The black hole's immense gravity would begin to pull on our planet unevenly. The side of Earth facing the black hole would experience a much stronger gravitational tug than the side facing away. This differential pull, known as a tidal force, would start to stretch our world. Initially, this would manifest as catastrophic earthquakes and volcanic eruptions on a scale never before witnessed, as the very crust of our planet begins to crack and deform under the strain. As the gravitational assault intensifies, our planet's protective layers would be the next to go. The atmosphere, a delicate blanket of gas held in place by Earth's own gravity, would be no match for the cosmic vacuum cleaner approaching. The black hole would begin to siphon it away, stripping the air from our skies and exposing the surface to the harsh vacuum of space. Following the atmosphere, our oceans would boil away into space, and then huge chunks of the planet's surface itself would start to be ripped away, pulled off in a stream of rock and debris, spiraling towards the insatiable darkness ahead. If Earth were to fall into a stable, yet dangerously close orbit around the black hole, it would face a different kind of torture known as tidal heating. The constant stretching and squeezing from the uneven gravitational forces would generate an incredible amount of internal friction. This process would heat our planet's core to unimaginable temperatures, far beyond its normal state. The surface would become a hellscape of molten rock, with relentless volcanic activity covering the entire globe. Our blue marble would be transformed into a glowing incandescent orb, slowly being cooked from the inside out by the relentless gravitational dance. This entire agonizing process would be accompanied by a lethal bath of radiation. As matter from our planet and any other nearby objects gets pulled towards the black hole, it does not fall straight in. Instead, it forms a swirling, superheated structure called an accretion disk. The friction and compression within this disk heat the material to millions of degrees, causing it to emit tremendous amounts of high-energy radiation, like X-rays and gamma rays. This radiation would be powerful enough to sterilize our planet long before it was physically torn apart, erasing any trace of life that might have somehow survived the initial chaos. The ultimate fate of any object falling into a black hole is a process with a wonderfully descriptive, albeit terrifying, name: spaghettification. This is the most extreme conclusion of the tidal forces we discussed earlier. As Earth gets closer and closer, the difference in the gravitational pull between the near side and the far side becomes astronomical. The planet would be stretched vertically, like a piece of cosmic taffy, while being squeezed horizontally. This intense stretching would pull apart every mountain, every continent, and eventually every single rock, until the entire planet is unraveled into a long, thin stream of atoms. The experience of spaghettification depends on the type of black hole. For a smaller, stellar mass black hole, this process begins hundreds of kilometers before you even reach the event horizon. The tidal forces are so extreme near these smaller objects that our planet would be shredded into a noodle of plasma and atoms, well outside the point of no return. For a supermassive black hole like Sagittarius A*, the tidal forces at the event horizon are gentler. An object could cross the event horizon whole, only to be spaghettified deep inside, where the gravitational forces finally become overwhelmingly strong. But in either case, the end result is the same: complete and utter atomic disintegration. The black hole's arrival would not just be a disaster for Earth, it would spell the end for our entire solar system. The intricate gravitational balance that keeps planets in their stable orbits around the Sun would be completely shattered. Planets would be thrown from their paths like billiard balls. Some might be ejected from the solar system entirely, sent hurtling into the cold darkness of interstellar space. Others might be sent on collision courses with one another, leading to cataclysmic impacts. The delicate clockwork of our solar system, which has persisted for over 4.5 billion years, would be reduced to chaos. Even the smaller inhabitants of our solar system would become deadly projectiles. The asteroid belt, a vast ring of space rocks between Mars and Jupiter, would be completely destabilized. Hundreds of massive asteroids, some over 100 kilometers across, would be pulled from their orbits and sent careening through the inner solar system. The chances of a devastating impact on any remaining planetary bodies would become a near certainty. All this material, planets, moons, asteroids, and eventually the Sun itself, would be pulled into the swirling accretion disk, adding more fuel to the black hole's radiant, destructive feast before vanishing from the observable universe. So what happens after our planet has been spaghettified and its constituent atoms have crossed the event horizon? The honest answer is, we simply do not know. This is the point where our current laws of physics break down completely. General relativity, our best theory of gravity, predicts that at the very center of a black hole lies a singularity, a point of infinite density and zero volume where space and time cease to have meaning. It is a concept that our mathematics can describe, but our minds struggle to comprehend. It is the end of physics as we know it. The journey into a black hole represents a one-way trip into the unknown. Because no information can escape from past the event horizon, we can never receive a signal or make an observation of what lies within. It is a cosmic-scale locked room, and we are forever outside of it. Some theories speculate about exotic possibilities. Could the singularity be a gateway to another universe? A wormhole connecting distant points in our own cosmos? Or perhaps something so utterly alien that we do not even have the language or concepts to describe it? These ideas are fascinating but remain firmly in the realm of speculation. The mystery is compounded by the clash between our two most fundamental theories of the universe. General relativity, which governs the very large like stars and galaxies, works perfectly to describe the black hole's gravity. Quantum mechanics, which governs the very small, like atoms and particles, works perfectly to describe the matter that falls in. However, at the singularity, You have a massive object crushed into a tiny space, and these two theories give contradictory and nonsensical answers. A complete understanding of black holes will likely require a new, unified theory of quantum gravity, the holy grail of modern physics. Ultimately, the fall of Earth into a black hole would be a story of cosmic annihilation, but it would end with the universe's greatest question mark. Our world, our solar system, and all of its history would be crushed out of existence at the singularity, compressed into a point of infinite density. From there, its fate is a complete mystery. It is a humbling reminder that, for all our scientific progress and cosmic exploration, there are still places in the universe where the known laws of nature end and pure, unimaginable mystery begins. The universe is not only stranger than we imagine, it may be stranger than we can imagine.